So this is the moment you've all been waiting for. No, not the end of the course, when we talk about black holes. So remember we said that for a neutron star, the star has to die with no more than about a couple times the mass of the sun, about 2.5 times the mass of the sun. Well, what happens if it dies with more than that? A neutron star doesn't collapse because the neutrons are snobbish and like, nope, not getting in my space. Now, the neutrons will get a lot closer to each other than those electrons will, because the neutrons don't have any electric charge. But the neutrons, they have a little bit of self-respect and don't want to get completely in each other's face. But if the dead star is more than about 2.5 times the mass of the sun, there is no force in the universe that can overcome gravity. And that will collapse literally down to a point. Imagine something heavier than a couple times the mass of the sun, literally being crushed down to a point. That is a black hole. Another way to think of this is in terms of general relativity. Remember we had our warped space-time? Remember we had a flat rubber sheet? And remember we said that if you had, for example, the sun, it would warp. Remember the elephant sitting in the trampoline? Well, what if we had something with a stronger gravitational field? It would make even a longer divot, deeper hole. And the deeper this gravitational hole, the harder it's going to be to get out. You do not play chicken with a black hole. Got it? Because remember, this is the curvature of space-time. Once you go in, you need to expend energy to get out. And at some point, you would need an infinite amount of energy to get out. You can't have an infinite amount of energy. You'd fall in. You'd keep falling till you get to the center. That's a black hole. Okay? So black hole is, imagine taking the warp of space-time and sort of like pinching it and pulling it down infinitely far. You fall in, you can't get out again. Okay? Nothing can get out of a black hole. You would have to travel faster than the speed of light to escape a black hole. Because you can't see it, because light itself cannot escape, that's why it's called a black hole. Okay? Now, I can draw a diagram of a black hole. Not like this. If you can imagine a sphere, I'm going to draw it as a circle. Okay? This is the thou shalt not cross here. You shall not pass, to quote Gandalf. Because if you do, you can't get out again. Okay? Again, don't play chicken with a black hole. Oh, I can get away. Oh, it's harder, but I can get away. Oh, man, it's really hard to get away. Ah! Okay? There's a point where you get too close to the black hole, you can't escape. That is something called the event horizon, because we cannot see events inside of there. That information cannot get out. Okay? It's also called the Schwarzschild radius, after the physicist who first came up with this concept. Now, this is not a circle in space. It's actually like a three-dimensional spherical boundary. You can't like sneak in from the back, okay? At the center, that's where all the matter got crushed. All the matter, several times the mass of our sun, gets crushed down to a mathematical point. And that is called the singularity. It's called the singularity because not only does the mathematics break down there, but our knowledge of physics breaks down. This is where Einstein's general theory of relativity breaks down. Okay? Now, what happens when something falls into a black hole? I get asked this question by children all the time. And the answer is, don't try this at home, boys and girls. Right? Let's imagine that for some crazy reason you wanted to volunteer for this one-way suicide mission. And let's imagine that you feel that, well, I'm just going to like enjoy my trip in. I'm going to jump in feet first because they tell you not to dive. So if we jump in feet first, maybe it won't hurt as much. No. Because your feet are closer to the black hole, they will experience a stronger gravitational pull. They will experience a greater curvature of space-time. Your head will not encounter quite as much. What that means is that your feet will be pulled stronger than your head. Let's think about this for a moment. Remember the medieval torture device called the rack, where we stretch people out? That's what happens to you. What happens is that your feet get pulled in faster than your head. If you fall in feet first, you actually get stretched out and ripped to shreds. The end. You die screaming. It's horrible. Don't try this at home, boys and girls. There's actually a name for this really cool, awesome, horrible thing. It's called spaghettification. Yeah, like spaghetti, like being stretched thin like a strand of spaghetti. Really cool. Now, you can't really do this experiment because there aren't any nearby black holes that you can jump in. But we can actually watch material falling into a black hole and see it being ripped to shreds, see it being spaghettified. And in fact, that's how we actually find a black hole. Because black holes don't emit any light, how are we going to find them? We're going to find them by their eating habits. Remember when I had that white dwarf which had the red giant near it, that material was spiraling in? Well, if you had, instead of a star orbiting a white dwarf, imagine you had a star orbiting a black hole. The material would also be pulled in. You'd also have one of those accretion disks, okay, as the material starts spiraling in towards the black hole. And remember, I said the material in the accretion disk gets very, very hot because of the particles rubbing against each other due to friction. And it gets so hot that it actually emits X-rays. So in order to find a black hole, we need several things to happen. We need to have a binary star system. We have an object that we can see orbiting around something that we can't see. We know that object is there because stars don't just walk around in circles, okay? It's not like your drunk star go home. It's not the way stars work. If a star is orbiting, it's orbiting something, okay? So we need to have a star orbiting around something that we cannot see. We need to have the accretion disk with the X-rays to help us find this thing in the first place. And then we have to rule out all other possibilities for this invisible object. It has to be something that's too heavy to be a white dwarf or a neutron star or anything else. It has to be more than about 3 times the mass of the sun. And the great thing about binary star systems is that through Kepler's laws of motion, we can actually estimate the mass of this invisible object. And that is how we have found many black holes throughout our galaxy. And we also have ginormous, humongous, like millions of times the mass of our sun, supermassive black holes at the centers of galaxies that are eating entire stars for breakfast, lunch, and dinner.